Rolling.
We good?
Yes, we're on. Excellent.
Okay. Hi, my name's Halee, and I'm going to be presenting on the paper by Hare et al. About the consequences of increased temperature in CO2 for phytoplankton community structure in the Bering Sea. So just a quick little overview. We'll be talking about the primary objectives, the methods and materials, results, and then do a little discussion. Okay. So the primary objective, you guys probably all got from the paper, is pretty obvious. They're going to examine how phytoplankton community structure in the Bering Sea change when temperatures and CO2 are increased to levels predicted for the year 2100. Okay. So in this experiment, they collected water samples from 2 different locations. So I just plotted these on a map so you guys can get an idea of where we're working. So with those water samples, they had 4 different treatments. They had high temperature, which was just elevated temperature alone. They had high CO2, which was elevated CO2 alone. They had the greenhouse treatment, which was elevated temperature and CO2. And then the ambient treatment, which was present day temperature and CO2. In the offshore water samples, they added iron. And this was an iron-limited, high nitrogen, low chlorophyll area. So iron was added to promote plankton growth. And in the shelf samples, iron as well as nitrate, phosphate, silicic acid, these were all added. And these were added because in the shelf water samples, they were just low in pretty much every nutrient. Okay. So, in high CO2 and greenhouse treatments, there was a reduction of 0.2 to 0.3 pH units relative to the initial values. In offshore, the algal communities were limited by nitrate and silicic acid. The diatom to nanophytoplankton ratio, which is D to N up here, was significantly higher in the ambient treatment, and the D to N ratio was lowest in the high temperature and greenhouse treatment. But the original water samples were dominated by nanophytoplankton due to the lack of iron. In the shelf experiment, the algal community was limited by nitrate. The ambient treatment had D to N similar to that of initial water samples, and the D to N ratio of all the other treatments decreased over time. So, in this graph, we have photosynthetic rates on the y-axis, right here, and then irradiance, which Nicole told us about, but if you already forgot that, it's the radiant energy received from the sun. So in the top one on the shelf, we see the 4 different symbols, which are here. The black circles are the greenhouse treatment. The white circles are the high temperature treatment, black triangles, high CO2, and white triangles are the ambient. So the maximum photosynthetic rates occurred in the shelf treatment, and they increased 2.6 times compared to the other 3. And in the offshore, the max photosynthetic rate increased 2.7 times in the greenhouse treatment and 3.5 times in the high temperature treatment. So we're going to focus on graph A first, because that's natural. Graph A looks at the phytoplankton biomass as chlorophyll A, and it's pretty consistent up until day 5, where the treatments start to separate. And ambient ends up being the highest, and greenhouse is the lowest. Okay. Next is B. This looks at fucoxanthin, which is a pigment found in diatoms, so this graph pretty much tells us diatom abundance. And diatoms were highest in the ambient treatment, and high temp and low CO2 declined to near initial levels. So graphs C and D look pretty much identical. C focuses on 19 hex. I can't really pronounce the full name, so we're just going to go with that, which is the pigment found in haptophytes. And D looks at 19 bute, which is the pigment found in pelagophytes, and haptophytes and stalagophytes are both types of nanophytoplankton. So graphs C and D tell us the abundance of nanophytoplankton. And both of them are highest with increased temperature. And that's for the shell. And for offshore, chlorophyll A increased in all of the temperatures for the first 6 days, with the largest increase being in the high temp treatment. But on the final day, the highest biomass was seen in the greenhouse treatment, and all other treatments decreased. So with B, high CO2 and ambient treatments, which are the triangles, were higher than the increased temperature with respect to glucocyanin, which just means that high CO2 and ambient had the highest levels of diatoms. And with C and D, 19 hex and 19 bute were highest in the greenhouse and the high temperature throughout most of the experiment. And an increase in 19 hex and 19 bute occurred at high temperatures because diatom nitrate reductase, which is the enzyme that catalyzes the first step of nitrate assimilation, doesn't function well at high temperatures, so diatoms can't assimilate nitrate at high temperatures. Increased temperature alone or with increased CO2 led to increases in algal carbon fixation, and the carbon fixation rates could double as long as photosynthesis was not limited by light or nutrients, which may provide a negative feedback loop with atmospheric CO2 by sequestering the carbon and the deep ocean via the biological pump. But shift from diatoms to nanophytoplankton kind of has some drawbacks. Nanophytoplankton are smaller than diatoms, so they sink slower, which means it would take longer to get the carbon to go to the bottom of the ocean. And nanophytoplankton cell abundance increased with high temperature, but the overall final algal biomass, as seen through chlorophyll A, was lower. And nanophytoplankton cannot support the current food web, so there would be a shift from the highly productive food web to a less productive one. A less productive food web cannot support the megafauna that is currently in the Bering Sea, which would cause the fisheries to pretty much collapse, which would have a big impact on our life.
Hello.
Questions?